All right. So we said on the vertical axis it was the average house price. And then Nyla asked if they're using vertical and horizontal instead of X and Y. And yeah, that's a good observation. So the vertical axis is usually called the which axis? The vertical? Is that X or Y? It's Y, good. So we could even label your vertical axis Y here and Y here, and then your horizontal X and X. Anybody find the typo yet? In the next one it says horizontal axis, but then it says vertical. So horizontal, this should actually say horizontal axis. So make sure you fix the typo. Okay, the horizontal axis. So axes is with an E, axes is multiple axis, and axis is one. Okay, so the horizontal axis is the left-right line used to measure data on the graphs, and in this case, the horizontal axis is measuring the what? The year, good. Okay, the scale. The scale is defined as the numbers corresponding to the units used on the graph. And sometimes scale is used to make a misleading graph. So if you look at these two graphs, they're actually showing the same data set. Can you see that? They're showing the same data set. So I want you to talk to your group now. Which of those two graphs is trying to trick you? Which of those two graphs is trying to trick you? Talk to your group.
Where was she at?
Which one was tricky, the left or the right? The right one is the more accurate one, or the right one is the tricky one? What's tricky about the right one? Okay. Okay. So that's interesting because you guys had very interesting conversations, but I don't think everybody agreed on that one. So some people are saying that this one is easier to read the numbers, and so this is the less tricky one. Could anybody make a case for the other one being the less tricky one? So?
The one on the left makes it look like a bigger jump than it actually is.
Mm-hmm.
Versus the one on the right where it's just like, it went up only like 2,000.
Right.
But the one on the left, it's like a more drastic
Yeah.
difference.
So I think you both ideas made good points. I hadn't even considered the first point you guys were making. I think they're both good points. But the one that is tricky is actually the one on the left because it is trying to make it look like there's a larger increase. This one is showing you accurately how much the increase is, and it's just a little bit. But I think it's a good point that the one on the left is easier to read. Okay? So the one on the left is trickier. So I'm going to write the left one tries to trick you into thinking the prices increased more. Okay, and the y-axis should start at 0. If you look at this y-axis right here, let's see, it's going up 100 each time. No, it's going up 1,000 each time. So the y-axis would actually start at 79,000. That doesn't make sense. So the y-axis should start at 0. All right, we have some vocabulary, and we're going to try to make connections between the vocabulary and the graphs below, okay? So we have x-intercept, y-intercept, and outliers. Actually, I don't have any axes on those graphs, so I can't make any connections there. I'll have to draw a new graph so that I can make connections. So if you have a graph, and it crosses your axes, remember this is your x and this is your y. Then we have an x-intercept. And we have a y-intercept. Okay, so your x-intercept is where the line crosses the x-axis. The y-intercept is where the line crosses the y-axis. And then we have a definition for outliers. So when you have a bunch of data points, remember we said we're going to be collecting bivariate data. So we're going to be graphing the x versus the y. When you have a bunch of data points, often they're going to follow a pattern, but sometimes you have one point that doesn't follow the pattern, and it's an outlier. An outlier in a regression are observations that fall far from the cloud of points, and these points are especially important because they can have a strong influence on the regression. So if you see here, there's an outlier. I want you to circle the other outliers. So on each graph, see if you can locate the outlier, and then I want you to circle it. All right, so you found your outliers. There's one. There's one. This one has like a whole little cloud of outliers over here. Then there's that one and that one. So you found them all, right? Okay. There's a lot of words down here, so I want you to take a look. We got to process this information. Ready? In number one, the outlier has a small influence on the regression line. So the line seems to still go between all the other points. It doesn't seem like this outlier is pulling the line towards it too much. In the second one, it says the outlier is close to the line, which means it wouldn't actually change the line that much. In number three, it says that the outlier seems to pull the line up a little bit. So basically, this line of best fit is created by all of the points. And so when all of the points are kind of in a trend, they're going to stay together. But if you've got an extra one up here, it's going to be pulling the line towards it. Sometimes an outlier is real, like, meaningful data, but sometimes the outlier just reflects either a mistake in data collection or just like a mistake in general. Let's see, this one over here, number 5, it says because the outlier is close to the trend, there's little influence. Actually, yeah, that's number 5. And then number 6, it says that the outlier is far from the rest of them, but it's still on the trend. So those are all interesting to note, outliers. Next page, correlation coefficient. So today we're going to be finding a line of best fit in Desmos, so we're going to be using our computers. And when we find the line of best fit, not only does it give us the data for the line, it also gives us this value for R. So R is called the correlation coefficient, and it measures the linear strength between the two variables. So the R value is going to be between -1 and +1. An R value of 0 means that these points do not line up at all. Okay? So if you see like all these points all over the place, kind of like, oh, I haven't seen that picture yet. Actually, kind of like all of these pictures. All of these pictures seem like they actually are very close to a 0. R equals 0 here. No correlation between them at all. Okay? These are also close to 0, but this is going to be a positive correlation, and this is going to be a negative correlation. So this one might be like positive 0.2, and this one might be like negative 0.2. But if you really have points that line up, you're going to either have a positive 0.9 or a positive 1, or you're going to have a negative 0.9 or a negative 1. So being close to positive 1 or negative 1 lets you know that your points are really lining up. Being close to 0 lets you know your points are really scattered.
Wait, being close to what lets you know it's lined up?
So it's a strong correlation. When R is close to 1 or -1. But if r is close to 0, then that's a no correlation. So, and then the next paragraph is just talking about when the strength seems strong enough. So in physics and chemistry, the correlation should be between 0.9 and 1, or negative 0.9 and negative 1. But if we're talking about social sciences, often you can be at 0.5 and still find a relationship. All right, you guys remembering this from Algebra 1, y equals mx plus b? Which of the letters is the slope? The m is the slope, right. And so if you have a positive slope, that's going to go with a positive correlation. So this here, you can see it's a positive correlation. It's also a positive slope. And then a negative correlation will be represented with a negative slope. All right, and then the thing that we're going to do today on Desmos is called regression analysis. So it sounds fancy, right? But we're just going to be using Desmos. Regression analysis determines the relationship between the values of x and the observed values of y, from which the most probable value of y can be predicted for any value of x. And then this last note is saying just because two things are related does not mean that one causes the other. Okay? So this note is a famous quote. The famous quote is, correlation does not imply causation. Okay, so just because two things happen and they seem to be correlated doesn't mean that one causes the other. All right, it is time to take out our computers for Desmos. During a solar eclipse, the temperature begins to drop as the moon comes between the Earth and the sun. The cooling temperatures up through totality of the eclipse are shown. Using a linear regression equation, predict the temperature at the 4-minute mark during the cooling. So we need to find the place when what is 4. Is it the x or the y that is 4? Why do you say that?
Well, it's right there.
Here?
Yeah.
Okay, so we decided here that this is our x and this is our y. Remember, we even labeled our graph that way, right? So we labeled time on the x-axis. So we want to know where the x is 4. You can kind of see it over here. We can kind of see, oh, it's going to be like less than 60. But we can find an exact answer algebraically by substituting 4 for the x. Now, before we do that, we actually need an equation. So we're going to back up for a moment and find an equation. Okay? So we know the equation of a line is y equals mx plus b. Sorry, I'll switch over so you can see what I'm writing. So we know the equation of a line is y equals mx plus b. So let's write that above using linear regression equation. Actually, you can put it below. That's good here. And now we need to substitute the numbers we found for m and for b. So we have y equals, instead of m, we're going to find the number down here. M is negative 4.4. So y equals negative 4.4 x. And then plus b. Let's look at b again. B is 75.1. Okay, this is the equation that we're using. And now we said that we want to know 4 minutes. So 4 minutes is the x. So we're going to take this equation and we're going to substitute 4 for the x. Y equals negative 4.4 times 4 plus 75.1. And now you can use Desmos to calculate this. Don't put the y equals when you calculate it. Just start with negative 4.4 times 4 plus 75.1. Okay, so I'm getting 57.5. Can anybody confirm 57.5 degrees? Excellent, okay. So at 4 minutes, it is 57.5 degrees Fahrenheit. Now for the intercepts, Desmos will do most of the work for us. Bless you. I want you to go back to your graph and click on the intercepts. Go back and click on the intercepts. I need the x-intercept and I can't see it, so I'm going to have to zoom out. So I'm going to use this minus button to zoom out until I can see it. And now I'm going to click on my x-intercept. Okay, that's my x-intercept. We need to say what it represents. It's not that hard if you think about it methodically. This is an x value, 17.068, that's an x value. And on the x-axis we have time. All right, so this is time. This is the temperature, the degrees, right? So this point represents at 17.068 minutes, the temperature is what? 0. Now, this only is happening during the eclipse. Do you think the eclipse until totality, do you think that that will take 17 minutes? I don't know, maybe. Probably not. Probably it's quicker than that. So maybe it never actually reaches 0 degrees. That's kind of cold, actually. Yes?
I didn't get that on my graph.
You got something different?
Yeah.
Check and see if Sal and Nyla have yours or if they have mine. Alright, so remember I had to zoom out with the minus, and then after I zoomed out with the minus, then I clicked on this point. You guys should do the same, okay? So we're going to write this down now. When the time is 17.068 minutes, the temperature is 0 degrees. All right, I want you to click on the y-intercept and try to interpret what the y-intercept means, and then compare with your neighbor and see if they're getting the same thing as you. All right, so I'm going to click it right here. It's where the line crosses the y-axis, and I get 0, 75.1. So I'm going to write that down. 0, 75.1. So 0 is the time, right? At 0 minutes, then what is the 75.1? The temperature, right. At 0 minutes, the temperature is 75.1 degrees Fahrenheit. I think you know what you're doing, so yeah, with this section, let's do the R and then you can go.
Thank you.
You're welcome. All right, correlation coefficient R. Let's go back because it tells us that in Desmos. So it says that our R is negative 0.0999. I'm going to write that on my paper. Negative 0.999. All right, here's the easy part. The R tells us if it's a positive correlation or a negative correlation. Is it a positive or a negative correlation? It's negative because the number is negative. That's so easy, right? Negative number, negative correlation. Now, if it's close to 0, it's weak. If it's close to +1 or -1, it's strong. Are we closer to 0 or are we closer to -1? Yeah, we're really close to -1, which means it's really what? Really strong. Okay, so we will say that it is a strong, I'm going to say very strong negative correlation. Nope, just one L in correlation. I'm going to start with a capital there. It is a very strong negative correlation. I'm going to give you some time to do the next one. Some of you have worked ahead, which is great. It's about an electronics sale and their weekly TV sales. When it asks you the slope and the y-intercept, we already said slope is M. What letter is y-intercept? B, good. Okay, so here's what you're going to do. You can either open a new Desmos so that you have the other one still, or if you do decide to close these out, something interesting happens when you add a new table. Oh, actually, this one's fine. Sometimes you get x2 and y2. All right, if you're getting x2 and y2, you may need to ask for some advice along the way as you do this. But if it says x1 and y1, you're good. All right, so I'm going to come around and see who needs help. You guys are working on the second example. Working on this one. So going back to the notes real quick. Why don't I have, oh, here it is. Good. Going back to the notes real quick. We have a new data set. We entered the weeks and we entered the number of TVs sold. And then we did a linear regression with the same equation as the top. Y1 tilde mx1 plus b. And now we're finding m and b. All right, and I'm just going to round to 2 decimal places. So my m is going to be 1.07. And my b is negative 30.04. What questions do you have about how I rounded that? Let me go back so I can show you. What questions do you have about how I rounded? Any questions? I didn't give you directions about what decimal place to round at, so it's okay if you chose another one. But what's not okay is that the m is not 1.06, and I'm going to go back to show you why. If you look down here at your m, if I want to round it to 2 decimal places, you have to look at the number after that. And if that is 5 or more, it's going to round your number up. So if I round to 2 decimal places, it's 1.07. Okay? All right, now I'm going to write the linear equation. Notice that when I write the equation, I don't write y1. Like y1 is just how I talk to Desmos. I write y equals. Instead of m, I'm going to put 1.07. X plus, nope, instead of plus negative, I'm going to put minus. If you put plus negative, that's okay. Plus negative is the same as minus. So y equals 1.07x minus 30.04. Now, I'm a little bit surprised by that positive slope because when I look at the data, it seems to be trending down, right? 18, 16, 17, 15, 11, 12, 11, 9. The data it was trending down, but I have a positive slope. What caused that positive slope? I heard some of you using that vocab word. What was it?
An outline.
An outlier. Good. The outlier caused that positive slope. And walking around the room, I heard some really good conversations about that. This outlier up here messed up our whole graph, right? So we could redo this without the outlier. That might be a responsible thing to do. But at the moment, we're going to finish answering the questions, and then we'll consider that. So is the equation, what do you notice about the regression equation? I'm just going to say that it does not match the points. And is it valid? I'm going to say no because it just doesn't describe the trend of the data. It's not going to be helpful in determining anything, right? All right, and I already know one person had an idea about why week 48 was different. Raise your hand if you have an idea about why week 48 was different. I see one hand over there, one hand up front. Ian, what are you thinking?
Black Friday.
And Henry, you were thinking the same thing?
Yeah.
And then I got that from Omar earlier also. So does that make sense? We're in November, right? Black Friday is the day after what holiday? Thanksgiving, when they have like all these sales, right? And so on Black Friday, they sold 43 TVs because it was a super good sale. So probably Black Friday is a good reason. All right, so if we wanted to see how our equation would change if we took that point out, we can go ahead and do it. Go ahead and take out that point and see if the line seems to match the other points pretty well. Should. Okay, so taking out that last point. Oh, it looks so much better, right? All right, so I'm just going to add this equation at the bottom of my notes. Okay, without the outlier. Y equals, let's go back and see, negative 1.27x and then plus 69.0. There you go.